Hello there and welcome back to this video series on control systems. We have seen root locus method and rules for constructing root locus. Several example problems are illustrated in the past videos to construct the root locus, and we have seen that using about 6 rules we can easily construct root locus for almost any transfer function very easily. We'll try to use this to explain what happens when a pole is added to the transfer function or a 0 is added to a transfer function. We'll try to explain that and show what happens when these are added. I would strongly encourage you to watch videos 43, 44, 45 and 46 before watching this. That way you will make the most out of this video. To consider what happens when you add a 0 to the closed loop transfer function, consider a closed loop second order system. A second order system has this kind of standard transfer function where omega n is the natural frequency and this zeta is damping ratio. Okay, and you know that if you apply a step input you get 1 over s here, and so cs is given over here. Now we'll consider another system T1. This is system T with input C, with input R and output C. You consider another system T1 which has the same input R but the output is C1. Okay, and we have an added term s plus alpha divided by alpha. Other than that everything else is the same. S plus alpha over alpha is the added term. Because you added the term, the output is no longer C but it is C1. Okay, we have chosen this divided by alpha because when s is equal to 0, the net gain here and here should be the same. That way it is easy for comparison. When s is equal to 0, you have omega n square by omega n square 1. Here also when you set s is equal to 0, omega n square by omega n square, they both get cancelled, alpha by alpha they get cancelled, and you are still left with 1. That is what we said. We have chosen it to be s plus alpha by alpha, the additional 0 to be s plus alpha by alpha, to ensure that when s is equal to 0, both Ts and T1s have the same value. For a step input, we can see that C1s will have an added s term. Okay, so what we'll do is omega n square divided by this whole is one term. If you expand it, omega n square by alpha into s, omega n square. If you do that, you have this plus this. Okay, basically you can see that this whole is Cs. If you go back and see carefully, this is Cs and this is also Cs. So the C1s is Cs plus s over alpha Cs. I would like you to pause and verify this to make sure before you go ahead in the video. We know that multiplication in S-plane is differentiation in time domain, and we take the inverse transform to see C1 of t is C of t plus 1 by alpha dc over dt. That is, when you add a 0, you see an additional term coming in 1 by alpha dc over dt. We'll just take one representative example with omega n 11 radians per second and the damping ratio to be 0.2 and plot the step response. The alpha at minus 10 is shown in the blue. Alpha at minus 2 is shown in the black, and the red is the original system. That is what we essentially considered is we have an original system something like this, to which we added a term s plus alpha and plotted the response Cs and C1s for two different values of alpha. Alpha is equal to -2 and alpha is equal to -10. We see that when alpha is -10, very far away from the origin on the left hand side, the original response and the response when 0 is added, both are kind of close together. But when 0 is very close to origin at -2, you have a pronounced peak. Okay, when alpha is very small, a pronounced early peak is observed, and in some situations this may be used to speed up a slow system, but this may not always work fine. People generally tend to avoid additional zeros near the origin. Okay. Similarly, when alpha is negative, the response becomes sluggish. That you can see here. When alpha is negative, s plus alpha means there is a 0 on the right hand side. Zeros on the right hand side make the system non-minimum phase. Generally, non-minimum phase systems, they are not very desirable because they may give what is called an undershoot. To begin with, the response goes in the opposite direction and then comes back into the right direction. Adding a pole to CLF, you can investigate in the same way. This is the original transfer function with original output, and then you add a pole at s is equal to -alpha. So the new output of the closed loop transfer function, you need to clearly pay notice to the heading here. We are talking about closed loop transfer function. We are adding a new pole. Pole is in the denominator. Okay, we'll try to plot the same and see. When alpha is at -25, far left in the real axis, on the negative real axis, you can say the blue and red are almost coinciding. Okay, whereas if you put it -0.5, okay, it is very different from the original system. Original system is red. This black is with a pole added at -0.5. The second order system is behaving more or less like a first order system, which is drastically different response. So we say when the pole added is far away in the left half plane, it has little effect on the response. When the added pole is near origin and on real axis, it dominates the response. Dominates the response in the sense that you see original system is red, this system is black. It totally transformed the response. Okay. The oscillatory response of the original system is completely changed and it's behaving more or less like a first order system when a pole very near origin on the real axis is added. Okay, so in general, try to avoid poles very near origin on the real axis because that is similar to adding extra integration. Extra integrations may not always lead to stability. You need to carefully notice the system behavior and then only add poles very near origin. So far we have been talking about closed loop transfer function. We will see what happens when we add a 0 to the open loop transfer function. So we considered a system here, k over s into s plus 2. You have a pole here, you have a pole here, and now you added a 0. You can see in addition to pole at 0 and pole at -2, you added a 0 somewhere here. Okay, it's very interesting to see the shape of the root locus plot. I would really encourage you to try and draw this shape. Okay, what happens when you add an s plus 4 in is this is the additional 0. Having an additional 0 has in general the effect of attracting the branches towards it. If you add a pole, the branches here are attracted towards the pole. In fact, the branches are going around it. On the other hand, if you add a pole, if you add a term s plus 4 here, the pole has an effect of repelling the branches. Okay, originally the branches are parallel to the imaginary axis, but adding a pole here repelled the branches. It pushed it away from this. If you put a 0, it will attract towards it. If you put a pole, it will push it in the opposite direction. So in summary, we say when either a pole or 0 is added to the closed loop transfer function very near origin, it has large impact on the response. When a pole or 0 of CLTF near the origin is on the real axis, it is called a dominant pole or dominant 0. On the other hand, adding a pole to OL to TF in the right half plane, it invariably makes the system unstable. And similarly, zeros in the right hand plane are called non-minimum phase zeros and may cause undershoot. I think that's all we have for now. Have a great day.